And before we start, there are a few announcements we'd like to make. Please switch off your cell phones and there will be a question and answer session at the end of the talk. So today we have amongst us Mr. Rohit Gupta. And Mr. Rohit Gupta is the IITian who is teaching the world science and mathematics through the simple medium of stories. He studied chemical technology at IIT Kharagpur, but unlike his peers, Rohit Gupta chose the less traveled path to become artist, writer, science historian, and storyteller, which he sums up in the word Compasswallah. Mr. Gupta has avidly pursued his dream of discovering the culture and concepts that shape science and mathematics. He is now extending his research work to the people through unconventional workshops that involve documentary films and conversations. Mr. Gupta's latest initiative, the Zeta Trek, is engaging hobbyists from across the world to solve the Riemann hypothesis, a long-pending mathematical problem. He is an unconventional genius whose efforts are realizing the purpose to make the science of his problem more therapeutic. So please welcome Mr. Rohit Gupta with a huge round of applause.
Thank you. If I keep the mic like this, am I audible? Okay. Okay. Just one correction to your very generous introduction. I'm not a genius. I mean, unlike a lot of people who achieve big things in their 20s, I've had to actually work very hard to know what I'm going to do. So I'm definitely not a genius. But yeah. Okay. So. For those of you who want to, who've never heard of it, I write a column for the Hindu Business Line in which monthly I write about exactly the same kind of things I'm going to talk about today. Usually those are addressed to a very general audience who have absolutely minimal, just like high school level background in science and mathematics. But this talk is specially designed for you because you are a science and technology institute. And I myself come from one. So, to begin with, I want to talk about, there's a lot of strife in the world right now about, with the word religion or ideas of religion or between religions. So I've always thought of mathematics as a religion. And how that happened, I want to tell you the story today. With all its pit stops and milestones. So where does it begin? We're going to begin when I was your age, when I had just cleared the IIT JEE and it was, to be frank, a huge disappointment because as a child, I had been extremely interested in science. I had my own chemistry and electronics lab inside my room, which I had built. My chemistry lab was 388 rupees. I still remember it because every bit and piece, meant something to me. But then as competitive exams came on, I had to forget about all of that and start preparing, Irodov and da-da-da. And then suddenly you enter, so you finish one rat race to be a first at this, to be the best at this. And everybody's saying, oh, you made it, now you made it, your struggle is over, now, your whole life is going to be a piece of cake. And the moment you enter the first year, the whole thing begins again. And I was like, I don't think I'm up for this. I don't think I can do this. And, so initially I just started finding ways how to cut classes, but somehow I made it the second year. That's now the second year's first 2 months are when you live with seniors for the first time, right? So, anyway, I'll tell you another story. So I'm in class of engineering design. My department was chemical engineering, which happens to be the single most boring discipline in engineering. I can attest to you. I can give you enough evidence of that. And I can debate over this for hours. Well, the class was industrial design. So basically, you have boilers in chemical engineering to boil some chemical or liquid, and then if there's a gas or some kind of steam coming out, you need a nozzle for that. We were designing that nozzle for 2 hours. So the exercise was that given a metal sheet of thickness 5 mm, design a nozzle with a diameter of 10 mm. And so you have to go through this very interesting iterative procedure. So it's like a feedback loop. You give it one value, like 5, 5.5 comes out, you loop it back, then 5.32, So you keep doing it until you arrive at some kind of optimum value. This kind of method is used in things like interpolation, which you might have encountered or will encounter in the future. But I had no idea what the hell I was doing or what the purpose of this thing was. So I raised my hand and I said, "Sir, I have a question." And he said, "What?" So I stood up. I said, "Sir, if this is a nozzle and the thickness of the sheet you're making it with is 5 mm and the diameter is supposed to be 10 mm, where is the hole?" So my professor looks at me and he says, "Rohit, sit down." And I sat down, but I still didn't understand why it was that my entire class for 2 hours was busy doing this whole procedure, which was entirely useless because at the end of the day, we found that the minimum sheet thickness, so in engineering design, you're given a manufacturer's sheet in which it's written that the minimum sheet thickness available in the market is 5 mm. So why were we doing those calculations to begin with? And I completely lost interest in chemical engineering at that time. The reason of so why this sort of happened, we will again encounter later. But here, basically, there is a philosophical conflict between one is mathematical certainty. What I was saying was logically correct. That if you have a sheet which you're rolling, whose thickness is 5 mm, to roll it, you cannot make a nozzle of 10 mm diameter because there's no space, mathematically speaking, for the hole. It's, but in engineering, you realize that if you are rolling the sheet, you're automatically somehow contracting it immeasurably so that that hole will appear almost because of the errors, because of the difference between mathematical exactitude and the messiness of reality. Right? Reality. So engineering is a messy kind of science. Even in physics, when they say we have discovered the Higgs boson, it's with 95% certainty. How many people read about the gravitational waves being detected? Okay, that's a 6 sigma certainty level. So in physics, it has become acceptable to have probabilistic truth. Okay, if I'm saying 2 equals 2, or a square equals b square equals c square in a Pythagorean triangle, it's not a problem. It's not like 5% true. Nobody in the universe can say it's not true. But when they said we detected gravitational waves from another galaxy, it's 6 sigma level. What is 6 sigma level? Is when the Dabbawalas are distributing food in Bombay and they lose one box in 6 million transactions, that's 6 sigma level. Right? So, at some point, this philosophical sort of drift happened where it became acceptable for truth to not be absolute. Okay, we'll talk more about that. But so I was constantly being disillusioned. Of course, what I'm telling you right now, I did not understand then. I was just a student. But a few days later, I was sitting in the TV room of my hostel, and so two seniors come in, and they say, "Hey, you want to hang out with us?" And I'm like, "Okay, these are the guys who hit me with the hockey and dislocated my jaw about 1 month ago. Do I want to hang out with them? Of course not." I said, "No, I think I watched Pink Floyd." So that's what was on TV, live at Pompeii, the 1 hour set at the Mount, so Pink Floyd performing at the top of Mount Vesuvius. And I was like, really, I was the only one in the hall. But then I said, maybe I should go and say hello. Ragging is over, they can't touch me anymore. I said, okay. So I went to the rooftop of the canteen where they were just lying down. These two guys were lying down, and they didn't look like the guys who had hit me with a hockey. So I lied down with them, and we started looking at the sky. For 20 minutes, nobody spoke. And suddenly, one guy asked me, "So Rohit, what are you thinking?" And I said, and we were looking at the stars. And I said, "That's very strange, because I'm thinking, I'm not sure if it's the stars that are moving or if it's my head." So these guys both looked at me like, "What? That's deep, man." I was like, "I don't know." Anyway, that incident, because it really is watching the sky at night. I take a lot of morning walks at 5 a.m. It's a very, very interesting experience, especially if you just sit down, or if you're going around a building, or if you just sit down and just look at one part of the sky, because in 15 minutes you can actually see this part of it. It's actually not going in a straight line. It's like this sort of circular arc it makes, and the whole sky shifts. And it's like sitting in a train next to a train, and suddenly that train starts moving, and you're like, "Where's my dad?" Because you think it's your train that's moving, and you like panic. But it's actually, so relative motion is a very tricky thing. Which is why for so many thousands of years, people thought that the earth was the center of the universe, and it was the rest of the sky that was moving. So essentially, because you could see Jupiter is the brightest thing in the night sky after the moon, the brightest thing. Now you can see Mars also. Now these guys move just like I said, and so these are called the wanderers. But in fact, so their position changes on a day-to-day basis. But if you go out in the morning exactly at 5 a.m., you'll see that the position of Capricorn, the position of the Orion constellation is exactly the same. So at the same time, the same stars will be in the same position. So people thought, they have certitude. These guys are fixed on some kind of infinite sphere, which is far, far away from us. But these planets are like sheep grazing on a sort of grassland. So they were called the wanderers. But anyway, that's about my first experience of astronomy, is to just watch the sky move and wonder what is actually moving. But anyway, after that night, couple of days later, I was bored and I went to the library in the hostel. And completely, entirely by accident, I found this book called Foucault's Pendulum by Umberto Eco. Have you ever heard of this name? Right? Umberto Eco passed away about 12 days ago. So I made it a point to bring this story to you of why this book, Foucault's Pendulum, changed my life. I had read crap like Sidney Sheldon and Jonathan Livingstone Seagull and all sorts of rubbish before this. this was the first real book I had read, which I read in one go in 3 nights. I couldn't sleep. I just had to finish the whole thing because of just the way it started. And it was talking about the same thing that had been bothering my mind about how the sky was moving. So, what actually is the Fuku? So, I'm showing you an image here. It's a 19th century, it's like early 20th century, which means from the 1910s or 1920s. It's a drawing of a pendulum that is hanging in the Paris Observatoire. It's a real thing. And the Foucault is not the philosopher Michel Foucault, but the physicist Leon Foucault. I'll tell you the relevance later. But I just love old historical images. So the book, Foucault's Pendulum, begins like this. That was when I saw the pendulum, the sphere, hanging from a long wire set into the ceiling of the coil, swaying back and forth with isochronal majesty. I mean, if you pick up a book on simple harmonic motion or oscillations and waves, they'll give you the equation and they'll say, this is the trigonometric way of expressing, simple harmonic motion. But isochronal majesty, like, you will never find this word, this kind of, poetic usage in a textbook. And, what I had never paid attention to in a mechanics class or at FITG where I was training for IIT or Tata McGraw-Hill book gripped my attention right away over here. This is science being communicated as poetry, as literature. Okay? And this was a completely alien experience for me. So, and he's giving the formula as well in the second paragraph. I'll give you time to read it. And focus on the last line of the last paragraph, we'll talk about that. So let's break this down a little bit. The time it took, so he's talking about the period of oscillation, right? By an arcane conspiracy, so by conspiracy he's talking about the equality thing, like where the equation has two left and right things. Between the most timeless of measures, okay. The singularity of the point of suspension, where the pendulum is hanging from. Now he's increasing this digit, singularity, the duality of the plane's dimension. Why is he saying that this pendulum is rotating in 2 dimensions? This is very interesting. Exactly, you got it. It doesn't, it's not 2 dimensions. The triadic beginning of pi. So pi begins with 3.141. Okay, that is actually a dimension, that's a number. It's not 3 dimensions. So first he's talking about singularity of the point of suspension, then duality of the plane, then triadic. It's just a number 3. What's triadic about it? Okay, this is very interesting wordplay over here. The secret quadratic nature of the root. Okay, so where is the quadratic equation in this? Is there a quadratic equation in simple harmonic motion? Sorry? Actually there is. If you solve it using gravity, when the mass is a vertical component and this component, so wherever gravity comes in, a square comes in, right? Because 1 by r square. Okay? So, and the unnumbered perfection of the circle itself. I think this is a beautiful paragraph, even though technically at some points it takes poetic license, right? But there's a beautiful way of looking at something which is usually considered so dry. So suddenly this was my first, it's wrong the way we are taught today of science as being something different, poetry as something for unintelligent and gay people, you know, and engineering for people who want to have a good career and you know, South Indians. So, so these things are a completely new phenomena. In the 16th and 17th century, it was not like that. Especially in the time of Newton, we will come to this, that the conspiracy here is actually against the human mind. That if you separate these people as these are the engineers, these are the poets, these are the authors, these are the policymen, you know, don't let them sit together, don't in the same room, don't let them talk, don't let them be everyone at the same time. It's, you know, divide and conquer. It's easier to control a civilization like that. This is the greatest conspiracy of the last 300 years. I want you to keep this in mind. I could have said nothing more political today than that. But I know we'll talk about something else later. Okay. So, we've already talked a lot about what is truth. Okay? So, a little bit more on that. Let's say, I mean, you're in love with someone and you say, you know, I love you. That's at that moment that thing is true. 6 months later, it may not be true. Right? Today I am the Prime Minister of this country. 2 years later, that may not be true. So these kind of truths, which are of a socio-cultural nature, which exist only in the human sort of realm of practical things and social things and the community, they are all like sand. They keep shifting. That's not the kind of truth I am talking about. I am talking about the fact that, you know, if something like, let's say, the Pythagorean theorem, right? A square, which you know, I don't need to draw it on the board, right? Okay. I still will because it will come handy in the future. Well. Now, this is, I'm going to give you a very interesting perspective on this, although. The Pythagorean theorem is not about the triangle at all. It's not about the triangle. It's wrong. It's wrong to look at the Pythagorean theorem as a triangle. The basic function of the Pythagorean theorem is to measure the distance between this point and this point. This point is just a reference. It's the basic measure of distance in two-dimensional space. Without this theorem, two-dimensional space itself would not exist. It's the kind of truth that exists here, there, wherever there is two-dimensional space, this has to exist. Even if two-dimensional space exists in your head, this theorem has to exist. This truth will not change 6 months later. It will not change if you move to Mars or to Andromeda galaxy or whatever. This is the kind of truth that Plato and a lot of people after him, especially mathematicians and scientists, have believed in. Everything else to them is not truth. According to me, that nozzle has no hole. Right? Because I believe in this kind of truth. Even the truths of engineering are somehow false for me. You know, a lot of people say, who are like, oh, I love science, they're like, you know, it works. That's why it's science, it works. Like, no, it's not science just because it works. That nozzle may spew out this thing, but its equation is wrong. Because that hole is unaccounted for. Right? So now again, one more thing. It's also dangerous to take from textbook to poetic analogy. Because now Puerto Rico is saying, you know, the pendulum told me that as everything moved, Earth, solar system, nebulae and black holes, all the children of the great cosmic expansion. The beautiful thing is he's gone from one single hanging pendulum to the whole universe. Okay? But he says, as everything in the universe moves, one single point stood still, a pivot, bolt or hook around which the universe. So he is saying that this pendulum is pointing to that place in the universe which does not move at all. So he's actually saying there is such a point in the universe which does not move at all. As far as we understand cosmology today, there is no such point. The universe has no center, so to speak. So this is poetic license, but it's still very beautiful. At least it makes you think about those things in a very interesting way. Now, so of course the pendulum is moving due to gravity, and it will, wherever you hang it, it will sort of oscillate in the same way. But so as we saw that Umberto Eco's fascination towards the pendulum, he was almost treating it like some kind of religious object, because from this pendulum he starts talking about universe, and the pendulum is speaking to me. It's like as if he's standing in front of a statue of Shiva or something, and God is speaking to me. So this feeling has not only been with writers and poets. It has been a standard feeling in most of the great mathematicians and physicists that have appeared in the field. It's a myth. Like Richard Dawkins is going with the God delusion, like Muslims are bad, religion is bad, banned religion. This was never what all the greatest scientists ever said. They were all driven by a religious zeal to discover something about the universe. So, for example, Newton's masterwork, which is the single most important, I don't even have to say maybe, perhaps, no, it was the Principia Mathematica, was the single most and remains the single most important achievement of the human mind in its entire history. And that it's a subject of another lecture why, but at the end of it, he says, all of this universe has been created. I am just a medium that has been sent to rediscover what the ancients knew, and this universe is ruled by the Lord God Pantocrator. It is actually written in that book. And he says that gravity is the will. It is the will of Pantocrator, that God, which is pulling the universe together into whatever he wants it to be. So it's the mind of, it's literally the will of God. Which is very interesting. Because why should Newton, now actually he spent only like a very short portion of his life doing mathematics. Most of the time he was dabbling in like thinking about God and Christianity and like alchemy. So, but why should Newton think all of this? Look at gravity in a very interesting way. You have a cloud, a nebula of gas, which starts coming together into its own. Okay? Because of the mutual pull of all these particles, they start attracting each other. They become denser and denser. Then they become something like Jupiter, which goes further, something like Saturn goes further. Then, millennia later, something like Earth. Okay? And it is due to the force of gravity that planets actually form. Okay? And once a planet has formed, what happens? What does gravity do? This is very interesting. How does life, how is it that for so many millions of years, life has managed to survive on this earth without being molested by asteroids? Of course, dinosaurs were probably wiped out with them, but how is it that we are still safe? In spite of so many rocks going around randomly in the universe, comets, asteroids, meteorites, right? So, there is something around every planet called the Roche limit, which is what is shown in the diagram. Okay? Now, if you remember, in the 90s or something, you can Google it, there were pieces of a comet there was a comet called Shoemaker-Levy. Okay? It went around the sun, and then on its way back, it made its way straight for Jupiter. And the thing is, it's an amazing image. That could happen. So what happened was, the comet comes in, it approaches the Roche limit, and then it breaks into like pieces, and then they go doom, 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 doom. They break into smaller debris and they go into Jupiter. Why does it happen? Because at the Roche limit, the gravity of the planet pulling the comet and of the rest of the solar system becomes equal. So the comet, which is once it is crossed, it doesn't know whether to go back or to go forward. It's like, so the whole thing gets torn apart. That's the Roche limit. So gravity not only forms the planet, it gives you a defense mechanism from asteroids and meteorites and comets. Isn't that amazing? Isn't that amazing? Right? So this is why, and again, if this planet keeps growing and becomes a star, and then the star becomes too big, again it's gravity which collapses it into a black hole, or maybe it explodes into a supernova. So all of this, the destruction is being done by gravity, the creation is being done by gravity, the protection is also being done by gravity. How would he not think of it as the will of God? Right? So all these metaphors have been playing in their minds. Okay, for 5 minutes I'll take a question because I also need to breathe a bit. If there's anything so far you want to ask me something about?
So I think I read about the Roche limit in I'm first year, it's second semester, and the first semester we studied about the Roche limit. I couldn't tell when the next is. But I think I remember they mentioned that over the surface or the volume of the body, the gravitational pull changes. I mean, like due to its relation with the radius or the distance of the particle, which is applying that gravitational force, which is why the object which is approaching it breaks down. So could you like elaborate what actually happens in the Roche limit?
The basic thing that happens at the Roche limit is that, see, in any solar system, it's not only the sun that's attracting Jupiter, for example. Every object is pulling every other object. And still it's so stable because those forces are weaker than the sun's. That's all. But if a smaller object comes at that boundary where it doesn't know whether to be pulled by all these other forces, like the sun or the earth or this thing, or to be pulled into Jupiter. So its mass begins to crumble, it just begins to break down. That's why it breaks down. This is exactly how the rings of Saturn have formed. So lots of these things got trapped in different layers. And it's like Saturn is basically a grinding mill, of just made of gravity. So, if you look to study Roche limit, the best thing is to study the rings of Saturn. Because here what has happened is, a small pieces kept coming in, they broke down, but they didn't go completely inside. They went into orbit, then some kept breaking down. So it's like almost like your Chucky piece when it types. It's amazing. But the answer to
How would it be made symmetrical around that object? Because the arrangement of other objects, celestial objects around, let's say, Jupiter, isn't symmetric. So
because see, all of this happens at the equatorial belt, because that's the thickest part, right? So even if you look at Saturn, the rings are on, they are a belt, it's around the center. That's where the Roche limit is, the force is strongest. Okay. But these are, also these problems have a lot to do with, so why are certain planets tilted in a certain way? How are accretion disks formed? These are not simple questions at all. This is again physics, it's not math. So, I may say something from intuition, but I may be wrong also. You have to go into the detail of it. I'm just telling you the intuitionistic explanation of how it may happen. But Of course, the Roche limit is a real thing because the equations of gravity themselves predict such a thing. Right?
So actually Roche limit, maybe in this case that might be what we are saying, but Roche limit can exist around any star. And like if there is only one planet, so that's the limit to which the planet can have a particular distance to that from the center of the star. Because actually what happens, the gravity at the end and the gravity at the other end towards the star, that is different.
Right.
So that like the planet loses its symmetry, it becomes oval.
Correct.
And then after that radius, it breaks apart.
Correct.
Difference in the force here and here. So that.
Yeah, so this is only one example. I'm saying I was only explaining the example of Jupiter. This, so Edward Roche, who came up with the Roche limit, there are many different. So, example, when you have two binary stars, okay, they have a different structure. It's like a lobe. It's like it's like this. So there are many different dynamics associated with this, but essentially, I gave you the simplest possible. But there are many different configurations possible due to the force of gravity in different systems, right? Okay, so now we were talking about why should scientists why should people like Newton have thought of scientific concepts in such a religious way? The thing is, it's not unique to European science or Indian science or Islamic science. I'll give you a beautiful example of Japan, where for centuries there has been a tradition called Sangaku. So we go to a Buddhist temple, Shinto shrines they're called. On the wall you'll find, instead of paintings of gods, you'll find these things hanging. So on the top, there's a geometric diagram. At the bottom, a question is asked about the diagram. Okay, and you can sit there and instead of praying to a god, you sit there and meditate on the problem. It's almost like thinking about the problem is like meditating or worshipping, right? So, which is I think a very beautiful way to spend your time in a temple. But let's look at one problem. Like I tried learning Japanese a few years ago, but I gave up after 6 months. It was so difficult. And my Japanese teacher's English was very bad, so he was translating everything wrong. But I have to start again. But anyway, I think there's a nice figure. It's not difficult to make out what it can. Would somebody like to take a guess on what this problem might be about? Sorry? Solar system. That's fascinating. I'll come back. Anybody? Any other guesses? Are you talking about this? Are we talking about this? Okay, phases. Okay, hang on. This is amazing. So, what did you say? What did I say? No. What is the first one? Solar system. Okay, second one was phases of the moon. Third one was atomic structure. Okay, that's interesting. So what I am seeing, okay, any other guesses? I think this comes in the same category, right? Phase of the moon happened due to partial eclipse. So, nobody else?
Some universal ratio or rule for any geometry.
Anybody else? Okay, I think this is enough. But this is amazing. This happens repeatedly in science. The same structure can represent many different things. When Bohr discovered or hypothesized the model, the atomic model, he was actually thinking of the solar system, right? So, saying solar system and atomic structure are not very different when you are looking at this object. Okay. Now, I think the correct answer, according to me, the phase of the moon is, I think, you were saying it because there is shadow on the white ball. Am I right? But I think that may not be the thing. So according to me, who said some ratio in 3D geometry? I think you are right. So I think what this is, it's a tetrahedron, you know that, right? A tetrahedron and a sphere is inscribed inside the tetrahedron. So what it's saying is, given a tetrahedron of side r, tell me the radius of the sphere inscribed inside it. Okay? Or the volume or whatever. And then it is saying, given the tetrahedron and the sphere, tell me the radius of the 4 other spheres you can fit inside it. Okay? That's what it looks like to me. But except there's only one problem. That there's one hidden golden sun kind of thing at the back. So that's mysterious. I don't know what it is. I can't read Japanese. But the interesting thing is this. So this kind of stuff was happening in Japan for centuries. And obviously you all heard of samurais. You watch the films, right? Right? Everybody's heard of samurai, right? So these guys, so they would go to these temples, and so every temple belongs to some kind of clan or family, or So when a samurai goes, you've seen every samurai wears this coat of this insignia of their family over here. A lot of these used to look like this, where there will be a circle, there will be smaller circles inside circles. Okay? Now, the cool thing, the most amazing thing about this is that Japan was completely closed for 300 years to the outside world until 1868. Okay? And suddenly they realized that the whole rest of the world has advanced miles ahead in terms of weapons and technology, and these guys are just sitting ducks in an ocean. So they have to quickly, rapidly advance. So I've written about this in an article called Death of the Floating World, but basically they called one major European scientist called Lord Kelvin, Kelvinator Fridge, Lord Kelvin, to send young physics students, and they started teaching who? Samurais. So samurai families now are not fighting anymore. All of them enrolled as physics students. Once they had done 2 years, they were sent to Germany and to Scotland especially, to Lord Kelvin's laboratory to train. Okay? So 1868, this process begins. 1872, the first batches of samurais go out. I'm talking not about like 10 or 20, I'm talking about at least 200 students. Okay? Going to Europe. So 6-7 years later they come back, they open their own schools in Japan. Okay? And 1905, so within 30 years, okay, Hantaro Nagaoka, one of the samurai kids, comes back from studying in Germany. He's hung out with everybody now, and he proposes a new model of the atom, where the nucleus is a positively charged Saturnian kind of planet surrounded by rings, just like Saturn, of negative charge. This was his model. Okay? And I mean, it was wrong, but the thing is, he was almost there. All he had to do was make them into particles and he would have arrived, which is exactly what happened with Bohr. But that's a different story. But the thing is that, when there were people thinking about the structure of the nucleus itself later, so in almost 30 years, Japan produces a samurai who's almost a Nobel laureate kind of level physicist. Isn't that amazing? Right? And very soon somebody wins it. That was Yukawa, but a little later. So these interactions between culture, religion, samurai, culture and Japanese religion, and then the way they used to have family insignia and certainly the atomic model, I find that very interesting. But this is, it's a good exercise for me. I should go and find a translation for this puzzle and find out if this really is a ratio in 3D geometry or what. So, yeah. How are we doing on time? Okay. So, this is the Yellamma temple in Karnataka. How many people are aware? You've seen fractals, right? All of you know fractals. So, fractal is sort of, would anybody like to define it in a simple language? You've all seen it.
You zoom in a fractal and you get a picture.
Yeah, so some kind of structure that keeps repeating itself at every level or every dimension. Sorry? The Koch snowflake, KOCH, or the Sierpinski basket, or the Chand Bauri, which is just outside Jaipur. It's like a stepwell which you saw in, I think, The Dark Knight, where, sorry? Yeah, he climbs out of that well. That's almost a Sierpinski basket. That's a fractal. What else? So you know the idea. So now the thing is, that's exactly what's happening in this temple. Is that so there's a basic structure at the bottom, and the same structure is repeated with in a lesser and lesser dimension. So it's essentially a zoom, right? So this kind of architecture has existed in India for centuries. And this is algorithmic. You can write a computer program. They were actually thinking in a computational manner. They were designing in a computational manner. Why? Was it easier to design that way? Were materials easier to assemble that way? There are 1,000 questions this raises. Right? So, but here again you see the combination of mathematics, religion, architecture, in architecture. If the whole internet died and only website that remained on the entire planet was the only one, I would prefer it to be dataisnature.com. There's almost 11 years of material there. Every single post, it's a blog, every post is gold. He's one of my best friends. But, I mean, it's like absolutely amazing stuff that there's an intersection of science, engineering, art, and computer science, everything. So, I mean, there are a lot of people like me, and like Paul, who are trying to bring all of these disciplines together again, because I look at a painting and I'm seeing like, oh wow, 3D geometry, you know, how did they twist it, right? So, these things are not separate anymore, at least in the mind of a lot of new thinkers. So, one more, so you've seen, I've shown you a Japanese example, I've shown you a South Indian Hindu example. Let me show you Islam. Because Islam is unique in its relationship to mathematics, geometry and science. There are many reasons. For example, when you pray, you have to face Mecca, right? So for that, there is a hole made in the mosque. It is called Qibla, right? How do you find that direction? You have to use a magnetic compass or something to find the accurate direction, right? But also, the earth has a sphere. And if Mecca is here, I am here, the compass will point through the earth. Right? It's not going to point like this. So, there is an intricate kind of geometry they have to understand, spherical geometry, just to point a mosque towards the correct direction. So, but anyway, essentially, the quick history is that while Indians were interested in numbers and number theory and algebra, the Greeks were also interested a little bit in that, but they were predominantly interested in geometry. Then Greek civilization collapsed, Archimedes was assassinated, the Library of Alexandria was burned, and then some of these texts were taken away and they found their way to Baghdad, where Islamic golden age started. And they started reading this stuff, and they're like, Euclid, oh my God, Aristotle, oh my God. And they were like, wow, this is amazing. And then they started translating and understanding. And then the only two instruments they had at their disposal was like a compass and a straight edge to draw. So the first script they invented for themselves was called Kufic. Now you can see it's almost rectangular in its design. So they design rectangular, we have straight lines and triangles. So it's extremely Platonic or geometric or Greek in its kind of look. And so is the architecture. The architecture of Islam looks exactly like its calligraphy. You see tall minarets, So, so Islam was born in the 7th century, at the end of like 700 BC, Muhammad declared whatever. And then for 200 years, Kufic script, this is called the Kufic script, it was the standard. And what were they writing with it? Mainly the Quran, right? And suddenly, as they started studying the Greek geometry, they started coming up with their own theorems. Al-Tusi, Ibn al-Haytham, these amazing Islamic mathematicians and geometers. And they started inventing new kinds of compasses and drawing instruments. So suddenly what happened was, the biggest thing Islam has, in Islam it was banned to portray any human or animal images. This is amazing. But you can't portray God in a human form. In Hinduism you can. It is done. But in Islam you cannot. That was until Mughal. In Islam, originally you could not portray, even today the big controversy Charlie Hebdo when they printed a portrait of home. But this is why all of their religious feelings came out through geometry. Okay? So you can see it in the architecture of Islam, you can see it in the calligraphy of Islam, and in the way they worship, because so the Qibla is one, but like really a few years ago, the Indonesian government released, or was it Malaysian? They released a manual for how Muslim astronauts can face Mecca if they are at the International Space Station. Think about that. Think about being a Muslim on Saturn, like, so. Okay, so because images were banned now, calligraphers, but this creativity, it has to come out. Some people, some Islamic cultures are a little more liberal. So, some people say, okay, you don't want us to draw a horse, I will not draw a horse, I will draw this. But this is a horse. No, it's not a horse, it's the name of Allah. It's a verse from the Quran. It's not a horse. So, this is how Islam dealt with censorship. Because human creativity knows no bounds. You can censor anything, you can do whatever you want. But the message is going to come out somehow here. No court of law can declare this to be a horse. So it's actually a verse from the Quran which has been drawn like that. So while the Islamic civilization was sort of declining, now this knowledge that they had got inherited from the Greeks started coming to Europe, which was just coming out of the Dark Ages. All the Inquisition and kill this, kill everybody, So world history is a very, very complicated, amazing thing. If your library has a book on the history of mathematics or any of the sciences, please go. I had a long conversation with Ayushman and Poonam in the cab coming from Jaipur today. I give them lots of tips on how to look for these things, so please take the help if you would like, or take mine. I will be available after the lecture. So now, meanwhile, what's happening is, so when new instruments arrived, and the artists didn't have to make square, perfect calligraphy, a new universe opened for them in terms of expression. Now, what was happening in Europe when this was ending in in the Islamic world? Okay. So give me just 2 minutes to catch my breath while you contemplate over this image. Is there anyone who is not immediately familiar with what this is? You know what this is? So for centuries, since Heron of Alexandria and even Indian Brahmagupta and all these, see, mathematics has come a long way in 4,000 years. When you swipe your credit card and buy that 200 rupee burger at McDonald's, what's going down that pipe hole is 4,000 years of algebra. We don't realize it, but it's there. Because when the Islamic mathematicians were working, they had no concept of negative numbers until that time. Neither did Europe. They were like, what is a negative number? So Brahmagupta had a concept, but it was very rough and not correct according to what we think of it. Because people will think, what? Okay, one is an angel, is -1 like a demon, right? How can you have this? What is a -1? I know that, I know what, sorry, what is your name? I know what an Abhishek is, but what is a minus Abhishek? Okay? I don't know that, right? So, it took a long time for people to come to terms with the idea that, okay, I can use negative numbers in an algebraically proper way and not appear like a complete maniac or mystic or, sorcerer. So, even that took a long time. But then what happened? Certain equations. So, okay, before that, let's take a step backward. Let's say you are a hunter-gatherer society. You have not settled down yet. So it will be very difficult for you to discover the Pythagorean theorem because you see the concept of distance has not actually occurred to you, right? You're just killing each other or going up and down tree. The moment you settle down and you are my neighbor and you open a farm next to mine, I need to draw a line, right? And suddenly I arrive with 500 horses and I say, okay, you two pay me tax according to the size of your land. I am the king of this village now. Okay? So you want to say, okay, how do I measure the size of my land? Or how will I measure the size of your land? So I will say, okay, his land is a square. So I will say this multiplied by this, right? But the thing is, let's say I can't do that. If the area is too big, okay, then all I can do is I want to know I don't just want to know this baseline, and then far away is a pole. I measure this, and I walk down. I measure the angle from here. Now I know enough about this triangle to calculate that distance. Okay, that's exactly how we measure the distance to a star, by the way. And how we do surveying in cartography. So they will discover this. But soon they will also discover that if this side is 1 and this side is 1, then what is the length of this side? This is again a very mystical, what the hell is the square root of 2? Right? How do you find out? So, I mean, when somebody, so Pythagoras, like, he was very religious about numbers and they didn't believe such a number, but they believed in rational, not in irrational. One guy proved that the square root of 2 is irrational. It has no rational representation. There is no x upon y which will represent the square root of 2 exactly. And that was a completely mystical, magical, unthinkable thing for them, that there is no p by q which will be equal to the square root of 2. How is that even possible? It's almost like saying -1 or minus some number. So, but they had to somehow people had to accept it. Okay, you proved that it's irrational. Now, over 200 years, we say, okay, let's accept these two exist. We'll just look away from them for a while. So, but then suddenly there's this guy called Cardano in Italy. He was a gambler, and there were these equation solving contests in Renaissance Italy, where a lot of equations kept coming up. For example, if I give you an equation, it's very simple: x square equals 1. Now, what this actually means is that suddenly a new kind of demon is emerging from the depth. Okay? Because what is happening is there are equations coming up which have terms, which are giving me terms, and I'm solving them like these kept coming up as I think people kept inviting no. But once you accepted like -7 or negative numbers, then you have to think about what the square root of -7 is. Right? Even Euler was like, what? I don't believe in this, or like. So a lot of people looked at it with skepticism. So there's a very beautiful quote by Leibniz, who is the co-inventor of calculus with Isaac Newton. But just read it. Like I'm showing you how the problem of negative square roots was a theological problem, a problem about God, right? A problem about religion, because that's what his religion was. We think that it's an amphibian between being and non-being. It's a beautiful language, again, like number 3 goes, which we call the imaginary root of negative unity. So he's talking about iota, which is the square root of -1. Now, for a long time, people didn't know what to make of it. But once algebraically you found that, okay, at least some equations which have something like A plus some term is appearing where if you have C whatever A minus, so this will eventually come out to some kind of non-complex number, okay, because it's essentially two conjugates. But apart from that, there was a surveyor called Caspar Wessel who realized that something strange is happening here. Why don't I say, because he's thinking about direction, he's thinking about how to measure all these things, and he knows that when I multiply the square root of -1 by the square root of -1, I get 1, right? So he says, wow, that's like 4 directions. Because it can be either, so I can have plus, so I can have north, south represent all the values of this the square root of -1, and if I keep multiplying by itself, I get north, south, east, south, west, whatever. So he started thinking of it in terms of direction, and suddenly, he published a paper saying, what if the square root of -1 is not a number, but a rotation by 90 degrees in the 2-dimensional plane? This is an amazing leap of imagination. But, so there is no talk, we are just doing algebraic calculations, there's no talk of second dimension over here. This comes out of nowhere, So, a completely new universe opened up, and suddenly you have the Argand thing where you have x and y. So Descartes' analytic geometry, which was treating coordinates, suddenly now algebraic equations become geometry. So suddenly algebra and geometry, which were not really the same thing, almost become they become mirror images of each other due to complex geometry. So this too was before complex numbers were accepted. This was a problem of belief. talking about all sorts of allusions to religion and belief and divinity by and in mathematics. Um, but let's talk about normal religion. Like, let's say in India, what kind of things do religious people expect from God? You know, when God does miracles, okay, that's the first thing everybody, oh, you know, I want a car next month, you know, so like a miracle. So what is a miracle? A miracle, how do you define it in some kind of logical, rough way? A miracle is something that happens contrary to all expectation, contrary to all the data in front of you. Okay? A statue of Ganesha starts drinking milk. A statue of Mary starts crying blood. You know, the water in Mahim Creek next to the mosque turns sweet. Everybody starts drinking that polluted stuff from, you know, the factory. So these are of course public, mass, consensual hallucinations. But what happens in the same thing in mathematics is contrary to expectation. Okay, I would say. You look at this square, this magic square. What is a magic square? It's very okay. You know that. Okay. So if I add the top row, 16 plus 3, 19 plus 2, 21, 21 plus 13, 34. I think so. If you every row, every column, and the two diagonals will sum up to 34. Now, what does that mean mathematically? It means, okay, one equation for the row, for each row, one equation for every column, one equation for two columns. So 10 simultaneous equations are being solved over here. And yet a solution exists. 10 simultaneous equations are being solved, and yet, so it's a constraint problem. Okay, but the thing is, the constraints on its possibility are very strong. This is not supposed to happen, and yet it happens. So this is why these are called magic squares. Like this is a 4 by 4 square. The 3 by 3 square, the smallest one, is called the low shoe square. It's worshipped in China. It's for thousands of years. They say that this river was flooding and then this turtle appeared. On the shell of the turtle was this 3 by 3 low shoe square. And it was like, wow, everything adds to the wow, this is God. Okay, so there was no flood after that. But essentially, so this kind of numerical stunt, I would say, has been considered a miracle by even normal people who had very little numeracy. They were like, wow. This is why people are so amazed by extremely juvenile stunts like, you know, Vedic mathematics and, you know, the multiplying stuff like, people are like, wow, how did you do that? And this is why like, people are like amazed by extremely ordinary things. But the cool thing about magic squares is like, you can say how many magic squares. Now we are thinking mathematically. How many magic squares exist in a 4 by 4 space? Is there a number to it? It's a question you can think about when you are free or bored. How many magic squares are in a 5 by 5 space? 6 by 6, 7 by 7, 8 by 8, 1 million by 1 million. Is there a relationship between how many magic squares exist in 3 by 3, 4 by 4, 5 by 5, 6 by 6, 7? Is there a mathematical relationship? You've got one of the most amazing theorems ever in the world. I don't know it, but maybe you can find it. It'll be like Fermat's last theorem or something. Okay? But this is how it begins. Thinking about mathematical problems. It can begin in a very simple way. That's the beauty of number thing. The problems are very simple, but it might take your entire life to solve them. The other thing is that what religions try to do is like, they try to solve a political problem of their particular time. This is what Christ did, this is what Muhammad did, this is what everybody does. they try to unite certain tribes saying, okay, let's unite under this common, these principles, and I'm your king now, I'm the prophet, but we are all going to gang up and fight these guys. Okay? And because they're different and we have to fight them or whatever. So, essentially it's a unification for some purpose. But in mathematics it's a little different. So, for example, algebra and geometry were two different objects throughout history. Algebra was about playing with symbols, right? A plus B, X, Y, and geometry was about playing with figures, right? But when complex geometry arrived, or when Descartes said, oh, you know, X and Y is a point in this space, in coordinate space. So suddenly they became one, right? So unification happened. That was also somebody saying like, oh wow, you know what, these two tribes come together. And in physics, what happened when Maxwell said that, electromagnetism and the same thing, and these things travel the speed of light, and then, so unification has been the theme of science. Like for a long time, electricity and magnetism were thought to be separate things. It took a long time for these two to come together, right? Now people are trying to bring together gravity and quantum mechanics. That is still separate. But unification hasn't happened. So grand unified thing. Unification is not a singular, it has been going on for thousands of years, is what I'm saying. And mathematics shows you that process. So these are also common features. Miracles happen. Like when Newton came out principle, everybody was like, how does one man come up with all of this and bring every separate strand of science together in one book? That is nothing. If somebody like Newton was born today, he would be nothing less than Jesus, a living God. I'm telling you, you don't have those now. But if that kind of achievement had been done in our time, in his time people were not as scientifically aware as we are right now. We would be amazed. So, this is another example. Now, things in how, so obviously like if you have a 5x5, 3x3, the structure of a chessboard is already there. Right? But who knew that magic squares are related to the game of chess? This was known to ancient Indian poets. I've written about it in a column called the Astronomer and the Chessboard. So here when something very interesting is happening, is the mouse showing? No. Okay, so from one, try and go to 2. You have to take a knight's jump. The knight has the most complicated play in the one chessboard. Are you following? Sorry. How do I fix this? Oh, it's connected by Wi-Fi. It's okay, we'll get back to that. If you guys have any questions in your mind, please feel free to ask in the meantime. Think about it. Or if you have any comments. Yeah.
Do you think that mathematics embedded in the universe or different way of progress of the human mind? Like now you said that this theorem is exists, so the distance between humans and our body space will exist. But at the time when we did discover this theorem, we still had alien beings. So you can say that it's just a one way of comprehending things, or like the universe exists because this theorem exists.
So, did everybody hear? Should I repeat his question? He's asking me that does mathematics exist with no regard to human existence, or is it a product of the human mind? Okay. So, yeah, scientists all over the world are divided because physicists like to think that the mathematical thoughts that we have are a product of the physics of the universe. That's what physicists like to think. Okay, but a majority of I don't like physicists, but a lot of mathematicians think that it is not a product of the human mind. Like we said, like suppose there's a nuclear war tomorrow because of some controversy over religion, and everybody kills each other off and like nuclear winter, this thing, and like 50 people remain, and Mad Max Free Road happens all over again. So there's a reboot of humanity, and suddenly they start settling down again. So they will again discover the Pythagorean theorem. They will again discover irrational numbers because they will start measuring land all over again. So I think it's not a product of the human mind. I'm a Platonist. I'm a neo-Platonist. I believe that mathematical objects are just waiting to be discovered, but this is a matter of philosophy. I can't prove this, but I think mathematical objects are waiting to be discovered. And I agree with a lot of mathematicians. Like I think they are the thoughts of the universe. They have nothing to do with this. We just happen to be smart enough to perceive those thoughts. When we should be lucky, and we should feel lucky about that. So there's nothing more beautiful than this, according to me. Yeah, Platonism is this belief which you just said that is there a mathematical reality outside of the human mind? Something like that. So it's a belief in mathematics as a world of its own, right? And there are various variations on that. You can, if you're interested in philosophy, you can look up Neo-Platonism and Platonism. I'm not really into philosophy. I think after a point, it's a waste of time. Philosophy is for, is this on video? Philosophy is for people who can't do math. Sorry?
You don't want the art and the math and
Yeah.
So what is, like, even I feel that there's no need to mix maths with art because other than it being beautiful, I think it will hamper the progress of mathematics because expressing maths in equations is easier than expressing it.
Can I give you an example? I can give you several, I can give you thousands, but I'll give you one example of how the arts help to propel, propel is like the art of mathematics. Can I give you an example? Okay. For thousands of, you've seen some, I've shown you calligraphy today, but if you look at really old paintings, you will see that like Egyptian hieroglyphs, they're completely flat. There's no sense of dimension, right? So when two people are talking like this, so there's no sense of depth. Like today, if you have in photographs, you have a sense of depth, right? That did not exist for a long time. Okay? But suddenly, I show in Mughal painting, you'll see this. In Mughal painting, two women are sitting, it's completely flat, but there, if you want to show one woman sitting, you just twist it like this, like you make the square a rhombus, and you'll feel, oh wow, there's some distance. It's like this seat has a length, right? Because that's all you need to do. Like, I mean, let's say I'm holding a square, but I can change the perspective by twisting the figure, right? Like, if this is a circle, but twist it, it will appear as an ellipse, right? So if I draw an ellipse instead of a circle, you think it's actually a dish, but which has been laid flat on a table. So geometry plays a role in creating the illusion of depth, right? So soon people started discovering new ways of doing this, and suddenly I could stand here and draw this auditorium. Like, so these, even if him and you are of the same height, when I draw it from here, he'll be larger and smaller, and these chairs will become smaller, and point where the camera is. So I'll draw this whole auditorium in 3D just by making everything smaller and smaller. That's perspective. Okay. Now, painters invented the art of perspective, not mathematicians. Actually, they were both. Albert Dürer and lots of his friends. They were the people who discovered this. But what impact did this have on geometry? Okay. The impact it had on geometry was phenomenal. I'll tell you why. Since the Greeks, the circle, the ellipse, the hyperbola, the parabola, these are called the conic sections, the various ways of dissecting a cone. They were considered a family of objects, but still different objects, right? But when painters started twisting these objects and giving them depth and this thing, some mathematicians realized, wow. So, an ellipse is just a different way of looking at a circle. A hyperbola is just a different way of looking at an ellipse. Or a parabola is just a different way of looking at a circle. So all these objects are actually the same, I just have to change the point of view. And a new kind of geometry was born, it's called projective geometry. It unified geometry in all of its aspects. It's considered one of the highest achievements in geometry. Like, there are geometers in the 1890s who said, Felix Klein, he said projective geometry is all of geometry. Okay, so never underestimate artists. They are capable of amazing things. Never underestimate them. Even mathematicians are artists. If we don't learn how to see, if two things are different, if we don't learn to see what's similar in them, like for example, can somebody tell me the similarity between the Pythagorean theorem and Fermat's last theorem? Do you know what Fermat's last theorem is? Huh? Okay. So, huh? Okay. Fermat's theorem is for Fermat's conjecture was, for what values of n is this true and has integer solutions? Like, for what x, like 2, 3, 4, 5, 6, whatever. But the power is n. So n can be 0, 1, 2, 3. But when I make n 2, what theorem is that? That's the Pythagorean theorem. So, mathematicians were able to see that the Pythagorean theorem and Fermat's last theorem are actually, this is just a special case of this. So I made a metaphor, an analogy, a bridge. This is an artistic way of looking at things. There's nothing mathematical about it. So, in fact, all of mathematics is like this. I'm looking at two different equations and think, oh wow, there's some similarity. I just said that how many 3 by 3 magic squares exist? How many 4 by 4? How many 5 by 5? I'm doing the same thing. I'm just increasing n from 0, 1, 2, 3, 4. That's all I'm doing. I'm increasing the scale. I'm trying to see the similarity in these higher and higher powers. Right? That's an artistic way of looking at things. That's exactly what mathematicians and artists do. So, have I answered your question? I'm very glad you asked this. A lot of people have this thing that arts, like people look down upon, like in the beginning I said, like poetry is for people who are not smart. I have met very smart poets in my life. I have written some bad poetry myself. But yeah. So this, go and look up Albrecht Dürer. He is one of the main people responsible for the invention of perspective. He was both a painter, one of the greatest painters of his time, and one of the greatest mathematicians of his time. He is the emblem of what you are asking me. How can art? This guy was both and great at both. Leonardo da Vinci, who is considered an artist, was living with Luca Pacioli, who is a mathematician. He drew his mathematical drawings. So, it's not, this bridge has been divided after the industrial age, where people have become machines. Oh, this is a toaster. I can't go to office sitting inside a toaster, right? Because you create different machines for every separate job, right? But, in China, people wash their vegetables inside a clothes washing machine. So that's creative, There's a very famous painting called Melancholia by Albert Dürer. I think next time if you guys call me, I'll lecture you on art. I will show you the relationships between art and mathematics. So we were here. Now what I'm saying is, this is a magic square. We know this. You don't need to sum up the rows and things. Just assume it's 260. And there's an algorithm by which these numbers are placed. I'll show you that beautiful algorithm. Go to 1. Jump as the knight jumps on a chessboard and go to 2. Jump as the knight jumps on a chessboard and go to 3. You can do the rest in your mind.
How do you decide which direction do you put the next point on? Like when you go from 3 to 4, why do you go from 3 to 4 and not 3 to 4?
That's a very good question. There's a particular algorithm to do this. So if you actually have to write a computer program for this. It cannot be done like by intuition. Just look up knight stool on Wikipedia, knight stool, and all of this detail is there. But what you're asking me is a very interesting question from a computer science point of view, but it's a little outside the scope of this topic, and I'm already running out of time. But it's a very good question. Okay, so we're going to the last part of my talk. But is there anything you want to ask me right now? Or should we go to the last part? Because after that I'll finish and then we'll talk. No? Okay. So I've shown you several examples. Algebra, geometry, number theory, everything coming together. And how everything is somehow special and was considered sort of divine or religious object of beauty. But then comes Isaac Newton. So I'll show you something interesting. This is the. So it's not like he just invented calculus in one night. The invention of calculus started with Archimedes and Eudoxus in ancient Greece. But it took so much time to come and become this full-blown supernova in Newton's mind. So this is a 23-year-old guy. That's why I said, when you introduce, I'm not a genius, that's a genius. I'm almost 40 and I don't think I've accomplished anything close to it. So, this is a time without calculators, without calculating machines, without computers. So what he is doing is, he has drawn a hyperbola like this. Okay? So this is one arm of a hyperbola. Now, he is trying to calculate the area under a hyperbola. What do you call that in calculus? Integration. He didn't call it integration, but that's what it is. So what he is doing is, he is dividing the hyperbola into equal rectangular strips. Okay. So I want to calculate it from here till here. How many strips will I need? Infinite number of strips, right? So essentially, every rectangle adds one term to the series he is summing up. Okay? Area of this. So he is summing up. So he is summing up 53 to 53 decimals by hand. Just imagine the patience of this man. Okay? But essentially 53 decimals is not exact in that sense. He's calculating the area, but you can go on. Because what happens is he's keeping this, but somewhere around here, there's a curvated, there's a sort of curved area which is assumed to be a right triangle. Okay, so some part of the thing goes missing. So, but the thing is, it's because it's a finite area. Area is finite, it's 1 point, but he's using an infinite series. He has introduced infinity into a finite object. Okay. So, but there's of course a culmination of a lot of work by a lot of mathematicians, people who've been working with infinite series, people who've been working with how to find the area of a circle, then parabola, then hyperbola, tautochrone, brachistochrone. So this has been happening for centuries, and suddenly he arrives and gives a method which is universal for all kinds of curves. Okay. So, now, when you are taught calculus in college or in school, first you are taught the concept of limits. Am I correct? That's pre-calculus, right? But that's how I was taught, and I was like, what is this? Why am I learning this? What does this have to do with my lunch? So, of course, I was not that shallow, but I am trying to. So, but the thing is that when Newton invented calculus, its foundations were very shaky because he had introduced infinity into a finite area. So, a lot of people were like, no, you can't do that. That sounds like black magic to me. And Newton must be secretly thinking, of course, I'm a sorcerer. So this was problematic, and it was only Cauchy and his contemporaries who solved this problem by inventing this theory of limits. But that happened much later. It happened almost 150 years after Newton. So, the sequence in which we are taught in college is something worth thinking about. It's not historical. It doesn't show you the logical flow of things. It doesn't show you the problem which is solved by this. first you should be shown the problem with calculus. Then why limits? You know. So anyway, so problems came with infinity and nobody knew, no, for 2 to 3,000 years, nobody has been able to arrive at a, what do you call, convincing definition of infinity. So then some people came and said, look, I think we have to stop treating infinity as a number. It's completely, it's just something else. So, sorry, I think so we have to stop treating infinity as a number. It's some kind of alien concept which we can't. A lot of people like. So you know why is infinity? Infinity has also been connected to the concept of God for a long, long time. So when in Archimedes' time, the king told him, since you are a mathematician, measure the size of my kingdom. So Archimedes wrote a short book on that called The Sand Reckoner, in which he's counting all the grains of sand in the universe. It's an amazing thing to read. Okay, and so he's contemplating of infinity, and he's trying to give some definition of it, like greater and all. And the king is like, wow, it's very big. So that's my kingdom. So when people say Jesus is the King of Kings, okay, what is the size of his kingdom? Every God, whenever you create a God, you have to show us the size of his universe. So even Islam, it says like, you know, and we have, the Quran says, we have adorned the heaven with lamps, you know, which is talking about the stars and he's talking about astronomy. But then they give some poetic allusions to the size of the universe, which Allah actually controls, to show how powerful he is. Every religion does that. So every religion has to deal with the concept of the size of the universe. Buddhists do it, Jains do it, Hindus do it, Muslims do it, Christians do it, Jews do it. Okay? So, and in Judaism, like there's actually a word for it called Aleph, which finally became part of Cantor's theory. So anyway, so Cantor came on this scene where nobody had understood this relationship of finite area, infinity, and the relationship between whole numbers, natural numbers. So he came up with this very interesting concept. He literally went mad in the process. He was in a mental hospital. This man was tortured, like he was insulted by a lot of his contemporaries. Today it's normal for us. It's very bad how we treat people. You know, even mathematicians treat their colleagues in a very ugly way. I mean, forget about. That's what I'm saying. Just even if you believe what facts I'm presenting you, say today all the religious conflict in the world disappears and mathematics becomes the only religion. People would still kill each other. I can guarantee. It will happen already. I mean, otherwise Cantor, a lot of people like him would not have been, in mental asylums. Boltzmann committed suicide. Ludwig Boltzmann. This would not happen. There's a lot of intellectual warfare going on where it turns really violent. I mean, driven to suicide is a form of indirect violence also. So I just want to give a very beautiful proof. It's called the diagonal argument of Cantor. Okay, he invented a method to measure infinities to compare them, and it's not difficult to understand at all. Okay. So, but try and understand this. Infinity is not a number. Okay. Good. Now I want to compare. Let's say you have the natural number 1, 2, 3, 4, 5, 6, 7 till endless. Okay? Infinity. We know they are infinite because all you do is keep adding. Right? Now take the even numbers. 2, 4, 6, 8, 10, blah blah blah. Okay? Now the thing is, I want to compare these two sets. One is the natural numbers themselves and one is the even numbers. Now normally you would think from 1 to 20 there are more natural numbers than even numbers. Right? There are some prime numbers, there are some odd numbers. You would say there are definitely more natural numbers than even numbers. But is that true for infinity? Cantor said no. Because wait, all I have to do is compare these two sets and make a one-to-one correspondence. If you have a friend, and I keep going on, and everybody has a friend and there is no end to this friendship correspondence, then both the sets have the same measure. This is an amazing concept. He's trying to say how these two infinity are equal. So, what he proves in the first diagram on the left is that the set of natural numbers, that infinity, and the even numbers, that infinity, are the same size. It's an amazing concept because infinity is not a number. It is something we don't yet know. And this is the beauty of mathematics. Do you think it's not a poetic thing?
Just the difference in how we map, like we're mapping 1 to 2, 2 to 4, 3 to 6. And in the previous discussion, we were mapping 1 and 2 to 2, 3 and 4 to 4, 4 and 5 and 6.
No. I'm not doing that. I'm just mapping one number to its double.
Here we are doing this.
Yeah.
But in the previous discussion, when we were saying that number of natural numbers is definitely greater than number of even numbers.
No. I was saying, given a limited set like until 20. Here we are not limited till 20. Here the correspondence will go on forever. Right? This parallel line will be always there. Right? So, since infinity is not a number, we are not dealing with 20, 30, 40 anymore. This infinity, it's not a number. At the end of time, that's not a number, that's not a size, it's immeasurable. Right? At that point, these two sets are the same. Okay? This is an amazing kind of idea of thinking about infinity. Did that make sense to you in some level? It will not, sorry? Yeah? So it's going to take some time to sink in, but the more you think about it will make sense to you. Infinity is not an easy thing to think about, there are lots of paradoxes. Okay? But as an idea, this was revolutionary and beautiful. People called him a heretic, like they called Jews heretics in the Spanish Inquisition, or they, whatever, in any kind of terrible whatever thing. So he was, mathematicians like said, this is ridiculous, how can you, but now it's accepted. And then he went further. So now he has proved that natural numbers, even numbers, the size of infinity are same. But what about irrational numbers, or let's say decimal? So numbers like this, like take 3 point. It has no rational representation, right? Once again, he came up with a very beautiful argument. He said that this infinity is a little different. Okay? Because here, I can prove that no matter what other set you give me, I can prove to you that there is more. So here's what he said. He said, so suppose this S1 to S11 is saying, but dot dot dot, that is the complete list, the infinity of irrational numbers. I can prove to you that there is one more, and one more, and one more. So how do you do that? He said, suppose this is the infinity of irrational numbers, 0, 0, 0, 0, 1, 1, 1, 0, like, so that, think of it as 0.000 whatever, and this is, so he's saying, now take a diagonal like this. Now, I'm going to take those diagonal digits, all of them, and flip them, 0 becomes 1, 1 becomes 0. That's, and he's listing this number. Okay. Now this number differs from each number in that list in at least one digit. Am I correct? Therefore, this number is not in that infinite list. So beautiful. Okay, that's how you prove that irrational numbers are a larger infinity than these numbers. That doesn't mean it's infinity plus 1, but it's a completely different kind of infinity. So, and then he went on to create instruments for measuring. It's a, I mean, master kind of, it's a amazingly abstract and beautiful piece of work. But this is, but of course, to be able to explain these proofs to you took me 7 days of understanding what the hell was going on in these. But I'm able to explain this to you in one slide because I spent some time on it. But I mean, the beauty of the argument is just amazing. The beauty, that's a very important concept in mathematics. Because usually what is beautiful turns out to be true. Which is why, so this kind of research, and it goes on literally mad. But I'm going to stop here.
Can you tell me how those numbers are arranged?
Sorry?
Can you tell me how those numbers are arranged? Like, what is the pattern?
In this particular case, there doesn't even have to be a pattern. It could be any list. All I'm saying is, it's the complete list of irrational numbers. The complete infinite list of irrational numbers. I can still create one more. That's all I'm saying. It's like saying, it's like an induction argument. So I'm saying it's like, this is an infinite list. Can I add to this infinity? Yes. It's a little abstract, but you'll get there if you study the thing again. There are some small points which I'm probably missing, but this is a well documented subject on the internet. So the diagonal argument of Cantor, you will find many articles on this subject. Many approachable articles as well written for general audience. You are of course not general audience.
So we actually have that as a part of our course.
What course is this?
Logic in computer science.
You will obviously have it. Because this comes into complexity theory. This is very important. So, okay. Now this is the same argument which I showed you, but it's a conversation happening between David Hilbert and this Cantor on the right hand side, that's Cantor. But just, it's a second example of the same argument, just for your visual. Right? Can I go forward? Okay. So now I'm not going to go very deep into this, but essentially, so now he had unified these different number systems, reals, irrationals, with his conception of what infinity actually is. But there were still many problems with the unification of mathematics. And finally, Gödel kind of came up with this again groundbreaking set of theorems which showed that even though most of the truths of mathematics are very universal, but if you try to build all of mathematics from a simple set of axioms like the ancient Greeks did, from a simple, like Euclid, that two parallel lines go on forever, and how two lines are not parallel lines. So if you break the logic of mathematics down to some very basic axioms, I'm not going to go into detail A, because I don't understand them too well, and B, because it's really complicated. But you know, there are some tutorials again on the net. We showed that mathematics cannot prove itself to be consistent. Okay, and there are of course corollaries to this kind of thing. So he broke this kind of. Some people say he broke the religion. Some people say he gave it a new god. But you know, that's where the story stands right now, with minor improvements that have been made on the way. But this is the story of mathematics as religion. So after Gödel, I'm going to end with a very beautiful quote by J.D. Barrow. Says, if religion is defined to be a system of ideas that contains unprovable statements, then Gödel has taught us that not only is mathematics religion, it is the only religion that can prove itself to be one. So I think that's really funny also. But yeah. So he's saying that religion is the only, mathematics is the only religion that can prove that it's a religion because it's inconsistent and unprovable. No other religion can so rigorously prove that it is unprovable. So that's really beautiful. Anyway, so we're going to end here, and that's the presentation. If you have anything more to say. You'll have to refer to a textbook or we can talk later about it, and I'll explain it. Like, I'll sit here for